Hello students. In this lecture, let us solve some of the problems on forced convection and here that too on external flows. So, first problem says air at 20 degrees under pressure of 1 bar is flowing over a flat plate at a velocity of 3 meters per second. So, it's shown here, it's a flat plate and air is flowing over the flat plate at velocity of 3 meters per second and the temperature of the air is given as 20 degrees centigrade. So, it is represented by T infinity as 20 degrees centigrade. If the plate is 280 mm wide, it is shown here at 56 degrees, that is plate wall temperature is 56 degrees TW. Estimate the quantities at x is equal to 280 mm. So at a distance of 280 mm from the leading edge, we need to find the following we need to find the following, right? So given the properties of the air at the bulk mean temperature. So whenever the air and bulk mean temperature are different temperatures, then first thing we need to find is to find the bulk temperature. So bulk temperature is nothing but TB equals T infinity plus TW by 2. T infinity is the air temperature plus wall temperature divided by 2 and get the bulk temperature. So bulk temperature obtained here as 38 degrees centigrade. So go to the properties table in the data handbook and obtain the values of rho, K, Cp, mu. Rho is the density, K is the conductivity, Cp is the specific heat and mu is the kinematic viscosity, which is nothing but mu by rho. Then we need to find the following quantities. First is given as boundary layer thickness. It is said as delta x, but in the data handbook it is given as delta hx. So both delta hx and this delta x are same. Then local friction coefficient, that is the friction factor at a distance of 280 mm, that is locally here the friction factor. Then it is average friction coefficient, so it should have been CFL bar, that is the average friction coefficient, that is average over the entire length. Then the shear stress, so you need to find the tau value. Thickness of the boundary layer, it is given as delta Tx. Then local convective heat transfer coefficient given as Hx, that is heat transfer coefficient at 280 mm. Then the average convective heat transfer coefficient, which is given as h bar, this is the average heat transfer coefficient. Then the rate of heat transfer is given as q, you need to find the q. Then the drag force on the plate, drag force is given as fd here. So first step, obtain the bulk temperature, and for the bulk temperature obtain the properties from the data handbook. Then since here these properties are already given, PR value is not given, so go to find out the Prandtl number. PR is equal to mu Cp by K. What is mu? Is nothing but mu into rho, that is density multiplied by kinematic viscosity into Cp by K. Substitute these values, get the value of Prandtl number. Normally the Prandtl number value will be varying around 0.7 for A for all the temperatures. Then first step, after obtaining the values, properties from the data handbook, next thing we need to know whether the flow is in laminar region or in turbulent region. So to find out that, first thing we need to find out is the Reynolds number. Reynolds number is equal to u infinity into x by nu. U infinity is the velocity multiplied by x, that is the length of the plate, divided by nu. So we obtain as 5 into 10 power 4. That means as the float starts from the leading edge to the trailing edge, so at the end of the plate, the Reynolds number is 5 into 10 power 4. That means which is in the laminar region. Since the critical Reynolds number given as 5 into 10 power 5. That means at the Reynolds number 5 into 10 power of 5, the flow changes from laminar to, or flow converts from laminar to turbulent. Hence, since the Reynolds number at the end of the plate is in the laminar range, let us find the values or the properties in the laminar region. So, these first thing we need to find delta x or the delta x, both are same. So, these expressions are obtained from the data handbook under the forced convection, so external flows and flow over the flat plate. So before watching this lecture, please go through the lecture regarding the formulas used in data handbook or the frequently used in the data handbook. So where the frequently used formulas are highlighted in from the data handbook. So now, using those expressions, let us calculate the required data. First thing is delta x is same as delta hx, or the hydrodynamic boundary layer thickness, which is given by 5x by root RA. So it is 5 into x is the distance 0.28 divided by root RE. That means square root of Reynolds number 5 into 10 power of 4. So that delta x is given as 0.0626 meters. Then find out the CFX value, that is friction factor. What is friction factor? That will be equal to 0.664 divided by root RE. So this is friction factor at a distance of 0.28 mm, and it is 0.664 divided by root of RE is given as 5 into 10 power of 4. So you will obtain this friction value. Next is the average friction factor over the entire length of 280 mm CFL bar. It is given as 1.328 divided by RE power x, the RE of x. That is nothing but 1.38 divided by square root of 5 into 10 power of 4. So you obtain this value. Then next is to find out the shear stress. Shear stress from the data handbook is given by as CFX into rho u infinity square by 2. CFX value is obtained here. The CFX value multiplied by rho density 1.134 and u infinity is the velocity is 3 meters per second. So 3 square divided by 2. So if you calculate, you'll get the value here in terms of Newton per meter square. Then next is thermal boundary layer thickness. It is equal to delta x divided by PR per 1 by 3. Delta x means this is delta hx, hydrodynamic boundary layer, divided by PR per 0.3. If you substitute, you will obtain this expression. That means the thickness of the boundary layer at the end of the plate is 0.007 meters. That means somewhere around 7 mm. Next, they have asked to find out the heat transfer coefficient. Heat transfer coefficient is obtained by using the dimensionless number, Nusselt number. This expression is given in the data handbook for constant wall temperatures. So nu x is equal to 0.332 Rex per 0.5 into PR per 0.33. And this new Nusselt number is given by Hx into Lc by K. Lc is the characteristic length. So if you substitute, you will get Hx equals Nusselt number into K conductivity divided by LC is the characteristic length. So this characteristic length varies, depends on the plate, or it varies for plate if it is for tube. So it varies differently. But for a plate, the characteristic length is same as the length of the plate. And this is obtained by the expression 4A by P, which is been explained in my previous lecture. So this Hx is given is equal to Nusselt number, which is given as 0.332 into Re, that is 5 into 10 power of 4 power 0.5 multiplied by Prandtl number, that is 0.7 power 0.33. That multiplied by K, K is the conductivity value, divided by the characteristic length. It is 0.28 meters. So you get the expression as or the value as 6.44 watt per meter square Kelvin. So this is the local heat transfer coefficient. That means heat transfer coefficient at a distance of 280 mm. Then next one, they have asked the average heat transfer coefficient over the entire plate length. So that will be equal to 2 times the Hx. So 2 times the Hx is 6.44. You'll get it as 12.878 watt per meter square Kelvin. Then next they have as the rate of heat transfer. So that is convective heat transfer. Convective heat transfer is obtained by the Newton's law of cooling. It says it's equal to H heat transfer coefficient into surface area multiplied by the temperature difference. So please make sure that the H value you choose here should always be the average heat transfer coefficient. Don't ever use this Hx value in while you calculate the rate of heat transfer. Please use the average heat transfer coefficient value. So it is, and in this problem it is 12.848 multiplied by the surface area of the plate, 0.28 by 0.8 into wall temperature minus the uh, air temperature, it is given as 36.3 watts. Next, we know that tau W, that is shear wall shear stress, is given by FD, drag force by area. So FD, drag force, is calculated by using this formula. So FD equals shear stress multiplied by the area. Shear stress is obtained in previous slide. So substitute that, multiply by the area, 0.28 into 0.28, you will get the drag force. Now, going to the next problem. Here it says air is flowing over a flat plate of 5 meters long and 2.5 meter width with a velocity of 4 meters per second at 15 degrees. So T infinity 15 degrees, U infinity 4 meters per second, width that is 2.5 meters, length 5 meters. If the rho value given is given as 1.2 and nu, that kinematic viscosity, is given as 1.47 10 power of minus 5 meters per second, calculate the length of the plate over which the boundary layer is laminar and the thickness of the boundary layer that in the laminar region. That means from as the flow takes place from the inlet, that is that the leading edge to the trailing edge, there's a, we need to find the location where the flow changes from laminar to turbulent, and that location is given as X here. Then the shear stress at the location where the boundary layer ceases to be laminar, that means shear stress at this location, that is at a distance of X from the leading edge. Next is total drag force on both the sides on that portion of the plate where the boundary layer is laminar. That means drag force on either side of the plate, again in this region. That means only in the laminar region. So first thing, to find out the laminar, that is given as FdX here. Tau x is the shear stress, delta x is the length of the, the boundary layer thickness in the laminar region, and X is the length of the or the distance from the leading edge where the flow converts from laminar to turbulent. So for this, first thing we need to know what is the Reynolds number at the distance of 5 meters, that is at the trailing edge of the plate. So that is obtained by using REL. L is we are taking as the length of the plate. So U infinity is 4 multiplied by the 5, that is length of the plate, divided by nu. So here it says it is 1.36 into 10 power of 6. That means Reynolds number at the end of the plate is said to be in the turbulent region, which is greater than the critical Reynolds number 5 into 10 power of 5. So that means, so from 0 to, it is going varying up to 1.3 10 power of 6. So that means at some location, there is a changeover takes place from laminar to turbulent. So for that, we need to find the distance x. So distance x is obtained by considering the Reynolds number as 5 into 10 for critical Reynolds number, because at this Reynolds number the flow changes from laminar to turbulent. So considering critical Reynolds number as 5 into 10 power of 5, that should be equal to u infinity, that is 4, that is velocity multiplied by the x, which you need to find out, divided by nu. From this you find the x value as 1.83 meters. That means from the leading edge at a distance of 1.83 meters, the flow changes from laminar to turbulent. Then, so it's given as at the length up to length of 1.83 meters, the flow is laminar and then converts to turbulent. So in the laminar region, we find out the boundary layer thickness as delta x, which is same as delta hx in the data handbook, is given by phi x by root re. If you substitute, you will get the thickness of the boundary layer. Then to find the shear stress, we need to find the friction factor. So friction factor in the laminar region at the location of where the flow, so that's why we converts from laminar to turbulent. So we take here Reynolds number as 5 into 10 power of 5, not at the end of the plate. We should not consider the Reynolds, because we are considering only the shear stress in the laminar region. So if you substitute, you will get this CFX value. So once you get the CFX value, the shear stress is obtained by CFX into half rho infinity square. So you know the CFX, half rho density value, you know 4 is the velocity, so you will obtain this tau. So this tau is obtained in the shear, is obtained above here is the shear stress at a distance x from the leading region edge. But they have asked to find the average shear force in the laminar region. So average means we need to take the bar. So 2 times the CFX, it is 1.328 by REX. So you'll get the average shear force, or sorry, shear average friction factor. Once you get the average friction factor, substitute in the shear stress equation, which is given as FD by A. So FD is equal to shear stress into area. But we know shear stress is equal to, so the average friction factor multiplied by half rho u infinity square. So that whole thing, this is the shear stress value multiplied by the area in the laminar, area of the laminar region. So FD, the CFX, which we obtained average, 1.878 10 power minus 3 multiplied by half into rho is the density, multiplied by u infinity is the first square. So then into area. So please make sure that area is not the complete area of the plate, only in the laminar region. Laminar region means length of the plate is 1.83 multiplied by the width is 2.8. So 0.083 newtons. So shear stress, shear force obtained above is only on the one side of the plate. So considering only the laminar region. So to find the drag force on both the sides, just simply multiply by 2, get the drag force on both the sides of the plate. Then in the third problem, they say air at 20 degrees centigrade is flowing over a flat plate which is 200 mm width. That is, width is 200 mm, length is 500 mm. The plate is maintained at 100 degrees, and find the heat loss, and the TS is nothing but the T wall temperature. Both are same here, 100 degrees centigrade. So what will be the effect on the heat transfer? Flow is parallel to 200 mm side. That means there are two cases are there. In first case, the length of the plate is 500 mm, width is 200 mm. In the second case, the length is 200 mm. That means plate is rotated, length is 200 mm, width is 500 mm. So two cases are there. For both the cases, we need to find the value of rate of heat transfer and compare it. So first thing we need to know is to get the bulk temperature. At bulk temperature, it is 20 plus 100 divided by 2, 60 degrees. From the data handbook, get the values. If is already given, then use those properties. If not given, go to data handbook and find out. Then First thing once you start the problem, then you need to find out at the end of the plate what is the Reynolds number. So first case taking L as 500 mm. So U infinity velocity. So velocity is 2 into L divided by nu. Get the Reynolds number. So Reynolds number at the end of the plate is laminar. That means throughout it is only in the complete plate, the flow is in laminar region. Since it is less than the critical Reynolds number 5 into 10 power of 5. So we need to use the equations in the laminar region. So use this again to get the HL value, heat transfer coefficient. See, HL is not the average heat transfer coefficient. This is the local heat transfer coefficient at the length L. Average is obtained by, like here, giving the bar. Okay, so first let us obtain the Nusselt number at the end of the plate. Is given by 0.332 REL per 0.5 into PR per 0.33 is nothing but HL into characteristic length by K. Characteristic length is 500 mm because at the end of the plate we are taking. So HL will be 0.332 into this Reynolds number per 0.5, Prandtl number per 0.33, they multiply by the K value divided by the characteristic length. So you'll get some value as 3.2 watt per meter square per minute. But we need to find the rate of heat transfer. So rate of heat transfer, we need to use the average heat transfer coefficient. So that's why we just multiply by 2 to get the average heat transfer coefficient. Then multiply by the surface area. So surface area is 500 mm by 200 mm, which remains constant, into TW minus T infinity is 52.8 watts. Then the case 2, where the flow is parallel to 200 mm side and this width is 500 mm side. So again here, again we need to calculate the Reynolds number because the length, the characteristic length will vary. So here length is 0.2, in the previous case it was 0.5, now it has come to 0.2 and it should be in meters. So Reynolds number, again here also it is in the laminar region. So go to the laminar Nusselt number, get the expression of this Nusselt number expression, substitute, obtain the HL value, that is H at this location at the end of the plate. So here it is given by 5.41, but the average H you have to take 10.83. So Q value is nothing but HL bar into surface area into TW minus T infinity. Here, since both the cases we are taking at the edge of the plate, so the plate surface area for both the cases is same. Only the heat transfer coefficient varies for both the cases. And again, temperature difference is same. So we'll get the Q value as 86.6 watts. Now, the next problem says air at 30 degrees and atmospheric velocity of 2.2 meters per second over the plate, which is maintained at 90 degrees. So length of the plate is 900 mm and width is 450 mm. So using exact solution, we need to calculate the heat transfer rate in the first half. They have not said whether in the laminar region or the turbulent. They have said in the first half, then the complete plate, then the next half. So again, as usual, go to the properties. For the bulk temperature, get the properties. Then to find the rate of heat transfer in the first half, get the X value. So total length is 900 mm. So it is 0.9, first half is 0.45 meters. Then find for the first half, get the Reynolds number. It is in the laminar region. It is less than 5 into 10 power of 5. So go to the laminar expression. Find the Hx value, nu x into K by LC. Then Hx we get, once you get Hx is the same procedure, get the average H value and X is equal to 0.45 and area, please make sure the surface area is only half of the plate because only in the first half we are finding the surface area. For that surface area, we are finding the heat transfer rate. So H bar into surface area is 0.45 into 0.45, width remains same, get the value of Q. In the next case, rate of heat transfer from the full plate. So full plate, it is 900 mm by 450 mm. Again, find the Reynolds number because the L, it depends on the characteristic length. So here also it is less than 5 to 10 power of 5. So obtain the HL, that is at the end of the plate, HL value. Once you get the HL value, again average, so you multiply by 2, then obtain the total length. So for the complete length of the plate, it is 149 watts. And so wherein you are taking area of cross section as complete length. So 900 mm by 450 mm. So but but Q for the first half is 105. So for the second half, you are taking by Q complete length minus Q first half as 43.84 watts. So this completes the 4 problems, and all these 4 problems is in the laminar region. So for problem solving on turbulent region, uh, let us do in my next lecture. We'll go and solve the problems on turbulent flows. Thank you.